it took up 4 lines, was we subtracted off the flow rate of the exit times the enthalpy of that exiting stream, the molar enthalpy. And then we use the flow rate of the exit. We're just relating it back to the inlet flow rate of A and theta and conversion. And it just simplifies out. Okay, so yeah, this is the enthalpy of species I in standard state at some reference temperature This other term is the change in the enthalpy resulting from usually increasing, doesn't have to be, but usually increasing from the reference temperature to the temperature that we care about. So if I'm at 200 Celsius and 1 atmosphere and I'm talking about water, what's the reference state for water? We'll say 25 Celsius, 298 Kelvin. And what's the phase? Liquid. So does that include phase change? Yes. This includes the energy of the phase change. Otherwise, this equation would not be correct, right? So this includes the delta H of phase change. I mean, if I have to boil the water, I have to boil the water. I can't ignore that enthalpy.
So you don't need a separate time for
It's inside H cubes. I mean, that's all I'm saying there is the way that we're defining this delta HQI would include things like CPDT, but it also includes enthalpy of phase change. Yeah, vaporization enthalpy, or yeah.
What's the last word over there on the right? Above change.
Above change, from increasing.
Okay.
From reference temperature to temperature. And it's not always increasing, but usually, because yeah, the reference temperature is usually like room temp. All right, and what's a usual definition for that term over there, HI? What do we often use for that? For certain things, yeah, but yeah. Yeah, I mean, I know what you're going for, but think back to like chemistry. How did you guys calculate delta H of reaction? There you go. Usually, what we do here is we put in the delta H of formation. So the formation enthalpies, everybody remember those? And then what's a normal reference temperature? Okay, so if we have no phase change, And what's this equal to? You were looking for it earlier.
Oh,
The integral from the reference temperature to the temperature we care about, Cp of that species times dt. And of course this is the constant pressure heat capacity. Okay. So what shows up in my energy balance, which we do still have, good, is the difference between the inlet and outlet. Molar enthalpies. So if we have these molar enthalpy equations that I just erased, right, there's a reference enthalpy for both the inlet and the outlet. So things get simplified a little bit. Oh, sorry. So the standard state enthalpy plus the integral from the reference to the temperature Cp dt, right? That's this first term. Subtract standard state enthalpy. Doesn't matter that it's at a different temperature in the inlet versus the outlet because this is the standard state. Here's where it shows up though. This is from the reference temperature to what temperature? Right. Now we're dealing with the inlet stream, so we have the inlet temperature. I left out the little I here. So the standard state enthalpies fall out, right? Everybody see that?
what did you write it?
Yeah.
Was there a stipulation here that you said the molar flow rate, something about the inlet and the outlet, or were you just subtracting it there? I thought you said some kind of stipulation.
No, no. This is just the difference between the two molar enthalpies of the inlet and the outlet. And you see that this difference, yeah, there's a sign difference, but it shows up in our energy balances. The stipulation here is that there's no phase change.
No, okay, that's what it was.
Yeah, because otherwise I can't use this simplified version of what is the molar enthalpy. I have to include the phase change. So you get, yeah, sorry, I left out one thing. Why do I need a little I here for the inlet temperatures?
Just differentiate.
Yeah, I could have two inlet feeds to my CSTR at different temperatures. Now coming out, is that possible? No, right? You're just going to have one, even if you had multiple feeds coming out, you'd still be sampling the whatever the mixed temperature is. Okay, so yeah, we have to have this I here, and then we get CPI dt. So again, this is no phase change. But now, it's not no phase change from the reference, but it's no phase change not between these two, but between the reference and the inlet for that stream or the outlet temperature. Yeah?
Why couldn't you cancel again, like once with the phase change, wouldn't the CP just go to infinity during the phase change?
Yeah, but you still got to include, I'm not sure what you're asking. You have to include the, for instance, the vaporization enthalpy of water. That would have to be a separate term. Yeah. You're right that the CP part, that's not going to change. That's still going to be there. Except now you're gonna have to deal with two heat capacities, right?
Isn't CP just DHDT? So
Yeah.
wouldn't it account for it? Because wouldn't the CP just go to infinity during the phase change?
You gotta. I'm sitting here having to review thermodynamics in my head. I mean, I know that it doesn't, but I can't give you a satisfactory answer right now.
Because as you add energy, the temperature doesn't change.
Oh, I know that the temperature doesn't change.
So then the CP
Right.
has to be infinity.
Right, but you still have to account for the enthalpy that you have to add in order to vaporize things. And I don't remember how it shows up. You guys had thermo last year. I had it 10 years ago. So somebody can help me out maybe, but I don't remember exactly how it shows up from the first principle. Yeah.
So with that or statement, like what if it was taken for no phase change from TR to TI naught, and there was a phase change in between TI naught and T?
I mean, all of these equations, this is simply a simplification of what we already know how to write out. You know how to write out the enthalpies with a phase change. You just have to add in the phase change term.
Okay, gotcha.
So you would just add those in. And they can still cancel out if there's the same phase change between the inlet and the outlet, right? So if you're going from steam water to steam coming out, the phase change terms cancel out, depending on the pressure. Okay, so where are we? So going back up to our energy balance, we can simplify this a little bit more. Because very often we're not going to be dealing with phase change. Right? I mean, who wants a reactor where you've got a